All right, thanks very much. Welcome back. So before I get to quantum computing, as I promised, I'm going to finish what I said in the morning. So I'm going to take about 5 or 10 minutes to say a few things about more SU2 and SU3, and then I promise we'll go through more fun stuff in a moment. Okay, so let me just remind you where we were with the formulations. So we talked about SU2 formulations, and we talked about the fact that if we want to really limit ourselves to the physical sector, which is much more efficient, things get complicated. Now I'm going to give you sort of an alternative. How can we keep things still local, but at the same time really reduce the subspace to a much smaller one? That is still not quite physical, but much closer to the physical subspace. So that's sort of some middle ground between the two approaches. So again, remember the SU2 gauge theory. Let's just focus on two sites for now. So I have site X, that's site X. Remember we had phi 1 of X and phi 2 of X as a SU2 doublet. And we had our electric fields on the left and here on the right side of this previous link, for example. And then we have E right X and then E left X and so on. Okay? So what I'm going to do now is to think about how I can build physical degrees of freedom on site. By physical, I mean only operators that are SU2 invariant, and therefore they already satisfy Gauss's laws, those non-abelian Gauss's laws. Okay? So the trick is the following. Consider the same theory, but in an identical formulation, and that's the Schrödinger boson formulation of angular momentum. So I'm going to think about a bunch of spin 1/2 objects, and each of those spin 1/2 has an identical Schrödinger boson harmonic oscillator representation. And in particular, if I'm sitting at this E left, because it's SU2, I have a doublet of oscillators. I have something that I call A oscillator number 1 at site X, A oscillator number 2 at site X. And associated with the right side of this link, I have B-type oscillators number 1, and then B-type oscillators number 2. If you have forgotten how it works, this equivalence between Schrödinger bosons and angular momentum, just look at your quantum mechanics textbooks, right? So there's a well-defined relation between the two. Now, both of your E operators and U operators can be written in terms of these 4 types of oscillators that I've defined on the link. So that's 4 degrees of freedom. In fact, I can reduce them to 3 because of this abelian condition on the link, because the total number of oscillators on the left should be the same as the total number of oscillators on the right, essentially because J or E left squared has to be equal to E right squared. It turned out that this would become a condition on the number operator A dagger A for type 1 operators, number operator for type 2 should be equal to the number of B type 1, number of B type 2 operators. Right, so that's an abelian condition. And similarly on this side of the link, I have A, or in fact B1 of X minus A, and then B2 of X minus A. And similarly here, I have another set of A1 X plus A, A2 of X plus A, and so on. Okay? And remember, I still have my phi 1 at X, and then phi 2 at X. Okay, so by itself, I can have this representation. Instead of working with angular momentum, I can work with harmonic oscillators. Sometimes it's useful, particularly if you have a quantum simulator that is completely bosonic. You can take advantage of this formulation. But I'm going to go farther, because this theory still has a set of non-abelian Gauss's laws that have to be satisfied between quantum numbers associated with the left and right side of this site, as well as the Fermionic quantum number. Those could be hard to satisfy on the states. So I'm going to go farther and define a set of SU2 invariant objects or operators out of these doublets. And you can do that easily. For example, this SU2, you can just use your dot products and your fully antisymmetric tensors to be able to connect all these like different combinations in an SU2 invariant way and get scalars or charge zero objects under the color. Okay? So then I imagine three possibilities. I can have fully bosonic operators, and I would call these loops. So for example, you can contract these two guys, or you can contract these guys together, and so on. So there are multiple possibilities. I can have a boson Fermion operator, which I'm going to call a string. So I can contract one of these guys with either these guys or these guys and make SU2 invariant objects. And I can have fully fermionic operators, and I call these hadrons. In fact, for SU2, it's just a meson. Mesons and baryons are the same thing. And which means I can contract these two and get my hadrons or mesons out of this. Okay? So these are still defined locally on site, but because they're SU2 invariant, you can show that they all satisfy the excitations that they can generate out of the vacuum would satisfy all those non-abelian Gauss's laws. Okay? You can do the same thing, exact same thing on this side as well and all other sides. And now the only relation that you have to keep in mind is the fact that there has to be still an abelian condition that should be satisfied in this link. And in fact, it turned out to be a condition between the loop and the string quantum numbers between the left and right side of this. Okay? So now I have a formulation, and I didn't write any operators, anything here. This is very qualitative picture. But I have a formulation in terms of gauge invariance local, not link local, rather site local degrees of freedom. And I have exchanged those complicated non-abelian Gauss's laws with just an abelian condition. So I really abelianized this theory by doing this theory work. Then all you have to do is to write all the possibilities, make sure that the algebra is complete, the commutation algebra is really complete. Then you start by acting with these operators on the vacuum of the loops, strings, and hadrons, and you generate everything else in your Hilbert space. And in the end of the day, you impose those abelian conditions on the link by hand so that you get your physical sector. Turn out that the size of this Hilbert space is much smaller than the original Hilbert space, and you have to have this abelian condition to recover the Kogan-Susskind theory in the physical sector. Okay? So then you take your Kogan-Susskind Hamiltonian, you turn it to a Hamiltonian in terms of only loop, string, and hadron operators. And those operators would only generate gauge invariant degrees of freedom. So that's pretty nice. Okay? Can you do this procedure in higher dimensions? Yes, you can. In fact, there is a very nice approach called point splitting. Let's say I have this, for example, site that is connected with these two links in 2 + 1 dimension. What you can do is to split this along an auxiliary third direction. Let's say a 3 direction. And then I still have my original directions 1 and 2. We put the matter site still over here at site X. And then we have done this splitting. And the reason for doing this splitting is essentially to be able to solve what is called a Mandelstam constraints on the sum of the angular momenta. Because if I want to make sure that the sum of all angular momenta is 0, I have different choices. I can either sum the J1 and J2 to 0, and then these two, and then all of them together, or maybe sum these two together and these two, and so on. And this is one scheme that would allow you to sort of uniquely define those gauge invariant objects. So then we have a quantum number that I would call, in this case, L12, another loop quantum number that is L31, L23, more quantum numbers over here, L prime 1, 2, L prime 2, 3, L prime 1, 2. And then there is obviously still the quantum number associated with the loops, strings, and hadrons. We call them NL, N, open, NO, and NI, incoming and outgoing strings, either this side or that side. And really, therefore, for each given site X, I have a tensor product of these quantum numbers, these quantum numbers, these quantum numbers. And there are a set of abelian conditions that have to be satisfied along the third direction, such that you get the exact same number of degrees of freedom that essentially you start with. Okay?
This is in one higher dimension at this point?
This is at the 2 plus 1 dimension. You can apply this to 3 plus 1 and more dimensions as well.
It's kind of reminiscent of some of the tensor network algorithms, which
Exactly.
this is this way.
Yeah. Yes.
Well, it's very SU2-ish.
Yeah.
So the formalism for SU3 is under development. The first 2 papers are out, and some very clever young people are developing even more along these lines. But yeah, for SU3, yes, you can have SU3 Schrödinger bosons, and you have 2 sets of them on each side of the links, because then the algebra, you have also the conjugate algebra, right, so the more quantum numbers. And then so there are more operators as a gauge invariant that you have to build, but there are papers where people have built these things now.
So there's the complete.
Yes. Almost common. I would say there is still a bit work to be done on SU3 higher dimension. SU2 higher dimensions are all complete. SU3 higher dimensions, the operators look complicated, and the others think that, and these others are some of my former postdocs, some other new younger people that have joined that collaboration, and Jesse Stryker, Indrakshir Chatari, Saurabh Kadam, and collaborators. They're working on coming up with even more simplified version of SU3 loop string hadron formulation.
Well, you say in principle SU3 could be done in any
Yes.
dimension.
Yes. That's the claim by these young people. And I can send a couple of papers if you're interested in that. Yes?
What about scaling up the number of fermion flavors living on the site? So right now we just have 1 electron. But if
Yes.
we have more, I guess the number of Gauss constraints doesn't change.
Doesn't change.
So
Exactly.
how does this LSH business work when you scale up the number?
So then you should ask these authors, because they're thinking about writing the next paper on multi-flavor LSH. So very good questions. These are research problems being figured out. Very good. Okay. Any other question? Yes.
This is for SU2 and SU3, but can I do for different groups? Or is
Yes,
it
I think in
unique?
principle, yes, although this is really based often the fact that there is this Schrödinger boson formulations. There are nice ways to form these invariants out of these objects. So for whatever group you have in mind, you have a similar, for U1 we cannot do that. There is no Schrödinger boson formulation of U1, so we're kind of stuck with what we have. But for this SUN gauge theories, there are these generalized Schrödinger boson formulations we can start with.
If I wanted to do quantum links, I would use fermions here, right, rather than bosons.
Yes. Okay. All right. So this is, again, not the only thing that you can do. There are a couple of very interesting papers that are coming, for example, from Berkeley group, a group of Christian Bauer and collaborators, when they're thinking about magnetic operators. So these are all electric-based operators, but we talked about magnetic operators. In that context, they're thinking about, for example, these 2-dimensional or 3 or higher dimensional theories, where it would have been nice, just as with the U1 gauge theory that we saw, that there's this Fourier space, it would have been nice if you have a dual formulation that would just characterize the degrees of freedom that are gauge invariant with these magnetic operators or plaquette operators, and we just build our Hilbert space out of those, right? So one way that you can think about it is to first fix as many gauges as you can, which is called a maximal gauge. So along each of these, you only have to fix. So this is unfixed, this is unfixed, unfixed, but everything else you can just set to 1. Okay, and we can even imagine periodic boundary condition. Okay, so then what they do is you can start from the origin and then define these magnetic operators. You can go around these three, and then have a variable that is defined like so. It only depends on this on fixed gauge degrees of freedom. You can define another variable that would go like so and come back and would only depend on this. And then you can, for example, go all the way up here and then come back, and then you only have something that depends on x. So somehow you're kind of breaking translational invariance. You better recover it in the end, so there are some tricks that are involved. But in the end of the day, you can just express your degrees of freedom in terms of these loops around the plaquettes that are connected to origin, okay? But what that means is that although your plaquette Hamiltonian becomes very simple in that formulation, your electric Hamiltonian is going to be very complicated. The reason being that you start from here to transform all your gauge to 1, and therefore, one by one, you have gauge transformations that are connected kind of to the origin. So then you have to kind of transform all those operators properly. It turned out that then you get electric field terms that could be very non-local, okay, in that formulation. This new variable, which is corresponding to the electric field, is going to be very non-local. So that's the price to pay. But again, very interesting development is that even in this picture, some of these non-localities you can deal with by borrowing ideas from this loop string hadron formulation, kind of trying to do some point splitting and define local degrees of freedom and things like that. So again, very recent developments just in the past few months. Some of these ideas are appearing.
These ideas are to reduce the, you can't get rid of it completely.
I agree. I don't think that they have a fully non-local local formulation exactly. So, okay, so this is all for SU2. I want to say just a little bit about SU3 before moving on, because I have to tell you what the representation of SU3 is, such that I can justify quantum computational cost of SU3. I promised you I will tell you what it takes to simulate QCD. So I have to meet that promise. Okay, so SU2 lattice gauge theory in the Koget and Susskind formulation. Let's forget about all these various different things that you can do. Just the simplest thing, which would be the irreducible representation or electric field basis for SU3. For those of you who have thought about SU3 group before, you are familiar with the quantification of quantum numbers of SU3. So this is irreducible representation basis. There are two Casimirs, which I'm going to call P and Q quantum numbers. I tell you the range of these variables in a moment. And then there is isospin associated with the left, and the third component of isospin quantum number associated with the left side of the link. And then there is the isospin associated with the right, TZ, isospin, third component associated with the right side of the link. And of course, hypercharge, Y left and Y right. So we have 1, 2, 3, 4, 5, 6, 7, 8 types of quantum numbers associated with the SU3. So again, this is the number of colors as expected. So instead of our J, M left, M right in SU2, we have now 8 sets of these quantum numbers. So the range of P and Q, they're going from 0, 1 to some lambda. So again, I'm going to cut it up. In principle, they're integers, but in principle, up to infinity, but I'm going to cut it off. And then T, L, T right. You just them from the notes so I don't make a mistake. So these are 0, 1/2, 1 up to 1/2 P plus Q, so. And then T, L, right, Z component is going to be minus 1/2 P plus Q, minus 1/2 P plus Q plus 1/2. So in units of 1/2, you go all the way to plus 1/2 P plus Q. Just because this is the third component of this guy. And then Y, left, right, is going to be minus 1/3 of Q plus 2P minus 1/3 of Q plus 2P plus 1/3. So in units of 1/3, you go all the way to reach 1/3 of P plus 2Q. Okay?
So this is, I think, so I can think of this as the Cartan generators plus the two Casimirs on the left and right.
Yes, exactly. Okay, so too many quantum numbers. The question is, what is the size of this bosonic register? You just figure it out based on this cutoff lambda. You're going to have 2 times, let's see, lambda plus 1. 2, let's do this. It's lambda plus 1 squared, and then you're going to have 2 lambda plus 3 squared, 4 lambda plus 5 squared, and then 5 lambda plus yes. So this is for P and Q. This is turned out to be for T left and right. This is for the Z component. And this is 6 lambda plus 7, which is for the hypercharged component. So for any given lambda, the number of possibilities you can imagine on that link is going to be this number, which is huge. Okay, so even for the crudest cutoff, which would be 1, and by 1 it means that you can have either 0, 0 representation or 1, 0 or 0, 1. So that's not a whole lot. And even for that, I think I have about 1.4 million states. Okay. Which sounds like a lot, but it turned out that it's only 20 qubits. Okay? So if you give me 20 qubits per link, I can fit this. Okay, so of course this is a very small cutoff. We want more, so just keep that in.
2 to the 20 is 1.4.
Yeah.
Yeah, okay.
Yeah.
It's just that, there's no other kind.
No, that's it. Yeah, exactly. Okay, so that's just like to give you an idea of how complex of the theory we're talking about when it comes to QCD compared to anything that I said so far. So then the question is, what is the E squared operator and what is the action of the U operator and this and this basis state? Let me just call this gamma lambda left lambda r. I'm just calling these two guys the representation quantum numbers, and then this set along with this to be this lambda, and then this set from this guy to be lambda, right? Just to abbreviate, okay? And this one turned out to be 1/3 of P squared plus Q squared plus PQ plus 3P plus 3Q gamma lambda left lambda right, okay? And then U on left R is going to be the sum over gamma prime, lambda left prime, lambda right prime, and then the dimensionality of gamma over dimensionality of gamma prime, and a bunch of Clebsch-Gordon coefficients, right? So now we want to sum. Okay, so this is in the fundamental, which means that it is 3 representation. It's a 3 by 3 matrix. This is the 3 representation. And therefore, there are indices 1, 1, 1, 2, 1, 3, all the way to 3, 3 associated with this guy. So I'm going to call those gamma left, gamma right kind of indices. Okay? And there is a correspondence between what these values are and 1, 1, 1, 2 indices of this matrix that I have in the notes. I think it's not important to just put it on the board. But in any case, then we have the Clebsch-Gordons of SU3. L prime, gamma, L3, 3 gamma L, gamma prime, lambda right, and then gamma lambda right, 3 gamma right, times gamma prime. Okay, so I think the most number of terms that you can get out of each of these components of the U matrix is going to be 12. So it's going to be the sum of 12 different operators at most for any given component of this matrix. And each of those 12 operators is going to raise or lower some sort of quantum numbers uniquely. And those quantum numbers are these kind of quantum numbers. Associated with those operators, there are Clebsch-Gordan coefficients of SU3, and these are tabulated. You can look them up. But now imagine that you want to compute them on a quantum computer on the go. So we'll come back to this point later. Okay? So once you have the action of your operators, you know what the action of Hamiltonian is, and these basis states. So in principle, we have everything to actually build a quantum algorithm to compute these, particularly when it comes to things like time evolution and so on. Okay? So any questions? So a bit technical, but in principle, if you've seen SU and gauge theory or group theory before, this should not be too strange, right? And the range of these sums and so on, everything is in the notes. I don't think that's necessary to go over it. Okay, so are we ready to talk about quantum computing? All good? Okay. All right. Okay. Quantum computing. So I have to tell you a little bit about the basics of quantum computing, so that's what we're going to do in a few minutes. So okay, so again, everybody probably is familiar with qubits, gates, and circuits. I'm going to be very quick here. Okay, so give me a physical state that is a two-dimensional Hilbert space, and you have control over that two-dimensional Hilbert space. You can manipulate it, you can have superpositions, and then you can have a coherent evolution of that qubit, meaning that you have really good control over that two-dimensional physical states. For all purposes, that's all I'm going to assume here. Okay? So a qubit is a two-dimensional Hilbert space. It has a wave function. It's in principle a superposition of two states, 0 and 1. And this is what is called a computational basis. Okay? Of course, there is also a block sphere representation of this. I can write this as cosine of some theta over 2, 0 is e to the I phi, sine theta over 2 of 1. And identify these states at any superposition as a point on a sphere that is characterized by the polar and azimuthal angles. Okay? This is for 1 qubit. For 2 qubit, you can have the same strategy, right? So you can have alpha 1, 0, 0, alpha 2, 0, 1, alpha 3, 1, 0, alpha 4, 0, 1, 1, 1. And we can also normalize our wave function to 1, the same here. So that determines the number of parameters. So there is one that is fixed by the normalization, And there is also another parameter that is fixed by the overall phase of that qubit, which doesn't really matter in the computations. So that's why instead of 4, here we get only 2 parameters, and then you can work it out for these other states. Okay, so then you can build higher dimensional states. Now, a gate is any unitary operation on the space of these qubits, whether a single qubit or multiple qubits. Unitary evolution or operations are natural for these quantum computers as quantum mechanics. So U acting on psi give a psi prime, and this is something that we can do in a quantum computer. So then, if someone would give you an arbitrary unitary and ask you to implement it on the space of these qubits, how do you do that, right? In general, that's a very non-trivial question. In particular, if we're dealing with n qubits, then there are exponential number of entries associated with that U matrix. So trying to find out the decomposition of that U matrix in terms of a set of elementary gates, in principle, could be exponentially hard. And that's really the art of quantum algorithm developments, to come up with polynomial scaling algorithms in the number of qubits such that you can do the task that you want with a given precision. Okay? So I mentioned the elementary set of gates. What do I mean by this? And the first thing to notice is that, well, if I have an arbitrary unitary in quantum mechanics and I want to estimate it with infinite precision, infinitely good precision, then I need an infinite sequence of gates. Okay, so that's not very useful. But an important theorem by Zohreh and KITP is the following. One can implement a unitary on n or a finite number of qubits with precision epsilon using a finite sequence of gates whose number would scale like logarithm to some constant power c of 1 over epsilon. And this is pretty efficient. Okay? Which means I can make my estimate of that unitary on n number of qubits arbitrarily closely, or arbitrarily well, but by a finite sequence that goes only logarithmically in the inverse of that precision.
How do you measure precision in these operations?
Very good. So there are different ways to define precision for the operators. So in this sense, you can define different norms, L1, L2, L infinity norms for these operators. I think no matter how you define that norm, then you get different, possibly explained here, but it's always going to be some polylog of 1 epsilon. But yeah, there are choices for those operator norms. Okay?
C is a function of n?
No. So it is always going to be a polynomial in n. It's going to be logarithmic in 1 over epsilon. Okay? Yes?
If you want to do multiple operations, will the errors grow exponentially with the number of operations, and then will that kill the logarithmic?
No, it doesn't go like so. It adds up, because if you have multiple of these, you can define a multiple of these as your new unitary, and then define a finite set of gates that would still estimated with logarithm of 1 over epsilon. Okay. So now the question is a finite sequence of elementary gates. So what are these? And it turned out that you can define a few sets that are universal, meaning that only by those building blocks I can build up any other unitary with this polynomial scaling in n, with logarithmic scaling 1 over epsilon. All of these theorems have very rigorous mathematical proofs. We're not going to go through that. That requires a course in quantum information. But just take it from me that you can do these operations using a set of universal, single, and 2-qubit gates. Or if you like, you can define a 3-qubit gates as well, if that helps, but usually single and 2-qubit is good enough. So what would be examples of, at least 2 classes of examples? One is the following. You can have things like R, X, Y, and Z gates, which are defined as e to the minus I, some theta angle, sigma x, y, or z over 2, just by definition. You can have something that is called phase gate, which is defined as 1 e to the I phi. And then what is called a C-naught gate, which is a 2-qubit gate, entangling gates. And if you're wondering what the matrix representation of this matrix is, it's on 2 qubits, so it's going to be a 4x4 matrix. And it's going to look like this. And then here you have 1, 1, 0, 0. So what this means is that, and the representation is the following. So you have 2 qubits. This is one of those qubits. This is another one. And I'm going to call this a C-naught gate, meaning that if the state of the first, this control qubit, is in 0, this doesn't do anything to the second qubit. If the state of this guy is 1, it's going to flip it. So that's what this part of the operation does. So it actually entangles the qubit. This is one way to entangle the qubits. Okay, so this is one set of universal operations. You can also work with another set that is a bit more like discrete type, because these are really continuous angles. How if I don't want to deal with that? Well, I can define something that is called an H gate, which is this one. This is a Hadamard gate on a single qubit, because it's a 2x2 matrix. What it does is creates a superposition of the 0 and 1, depending on whether it acts on the 0 state or on 1, gives you different phase between them. Okay, so this is what causes superposition for you in the circuit for 1 qubit. And then you can have Hadamard and then a T gate. T gate is 1, 0, 0, e to the I pi over 4. And then the C-naught gate, which is what I've defined there. Okay? So where do you think in these universal set of gates the quantumness comes in? Because classically I can define these operations on bits too, in principle. Can I? I mean, we have the NOT operation in the classical computers, right? The controlled NOT operation.
You don't have phase factors.
Very good. So not just phase factor, the continuousness is something that is very important, right? So that gives a very important lesson that if I had only something like this gate and this gate, and not access to something like this, it turned out that this is classically efficiently simulatable, because these are Clifford sets. You always need at least one non-Clifford gate in your set of universal gates so that you can do all unitary, quantum mechanical unitary operations. And that's the T gate or transversal gate. And it's interesting that by, again, finite set of operations of this sort, you can actually build that continuousness up to precision log of 1 over epsilon. Okay, so usually what happens is that, so of course if you have access to this set and you have infinite precision setting these angles would have been nice, but that's not very error-corrected way of doing this, it turned out. It is always better to have discrete finite sequence of gates such that if an error somewhere happens, you can detect it and correct it. So it's better to actually work with these kind of sets of gates. And therefore, in order to then generate a continuous unitary, then you need many, many of operations of these sorts. how many of them? Logarithm of 1 over epsilon of them. So this is called a gate synthesis in the fault-tolerant era of quantum computing. We want everything to be synthesized in terms of a finite sequence of discrete gates such that we can error correct them. But that means that then these gates are expensive ones. The transverse gates are the expensive ones. These are the ones that are building that continuousness for us. So something to keep in mind. In the near term, sometimes you hear people talk about entangling gates to be hard. And the reason is that they are, at the moment, slower than the single qubit gates. If they're slower, that means that if you have many of those operations, it's going to be beyond the coherence time of your hardware. And therefore, those are the costly operations in the near term of quantum computers because we don't care about error corrections and discrete set of gates and things like that. But in the far term, really CNOT gates are not that bad, right? We're assuming that we have reached the fault tolerant threshold and all these gates can be reliably implemented. Then it comes to how many of them we should implement such that we reach a certain precision, and these T gates turn out to be the costly part of the computations. So something to keep in mind.
I would assume that this is very sensitive to your hardware architecture,
Absolutely, but at the moment, all the hardware architectures have that in common, that entangling gates are more noisy for them at the moment.
2 qubit gates.
There are 2 qubit.
Or
These T gates, I times pi over 4.
why is it hard?
Because in order to build any unitary up to a given precision, you need these transversal or non-Clifford gates to be part of your set, such that you can make that continuousness that is in the quantum mechanics, right? There's like infinite dimension, sort of these continuous amplitudes that we have to build. And therefore, these ones need to be applied many, many times to build that continuousness for you. You cannot do it like for these sets.
So they cover the loss.
Exactly. So the Clifford set of gates, you can always efficiently, classically simulate those, but non-Clifford ones you cannot, and this is a non-Clifford. Yes?
Is that phasally optimized, or do you expect it
It could be in principle, I think, anything, but I think this is what people have worked out. But yeah, I'm sure you can define other non-Clifford transversal set of gates. But yeah, I'm not quite sure why this one.
The problem is that you have to apply it many times to get it full coverage.
Yes, exactly. Yeah.
Sorry, 2 questions. If instead of removing T, if you had H and T but you remove C naught, then is it classically simulated?
If I remove T?
No, there you did remove C. If you kept H and T but you removed C naught.
No, you need the C naught. You need your entangling gate.
Interesting.
Yeah,
So
you really need
removing
to.
any of them makes it not classically.
Yeah, so this is a minimal set of universal set of gates that can build that unitary up to that precision for you.
Then it sounds like all 3 of them are equally important.
All of them are important. But I'm saying that if you were just only interested in classical simulations, you could have done that with these sets of gates.
With any 2 of them.
Yes. Well, I think this and this. You need at least one entangling gate to build all the entanglement, right?
I have another question.
Yes.
So I'm still puzzled about this 1.4 million distance. So if we
This one?
yeah, so
Okay.
we're saying that it's 1.4 million states if you have one site, and if you have 2 sites, it would be 1.4 million squared. Right?
Squared.
And
Yes.
if you
It's
have 10
exponential.
sites, it would be exponential.
Yes,
So,
absolutely.
but that would make it impossible to do any classical lattice simulations ever. Some people.
That's why we don't do classical Hamiltonian simulations of QCD. We're doing efficient polynomial time Monte Carlo simulations, which are based on very different strategies.
Okay, so the classical calculations that people do with lattice is exponentially faster than this.
Depends on observables. If you're interested in real-time dynamics, we cannot do it classically
I see.
because of the sign problem. But yeah, for certain observables, absolutely. That's why we do it, right? This path would have been completely infeasible to go along.
Okay, so
That's why it was developed in 70s and 80s and was never really used right, in actual computations, until now that we might have these quantum computers, right?
I mean, there's a problem with shared logic, and that's matter physics.
Absolutely, yes. Any physical system, right, that is quantum mechanical, it just makes sense to map it to a quantum mechanical machine than a classical one. So we'll get to the cost of that quantumly if I get time. So I have to really...
Quick question. Maybe you said it, but so is the idea that to get any continuous unitary, you can get a sequence of the discrete ones and get that? But is there a unique choice, or there are multiple choices given?
There are multiple choices.
And then you would optimize based on which one is easy to, okay.
Exactly, yes, indeed. Okay, so let me now quickly talk about the mapping of fermions and bosons. So this was supposed to be only 5 minutes, because but this 5 minutes in principle is a 1 semester of quantum computing course, no? Okay, so what else do we need to know before we can do any quantum simulation? We have to know how to map our degrees of freedom. So mapping fermion and bosons. Okay, let's just start from fermions. Okay, so if I have a non-relativistic spinless fermion, which is just one component, or I have my Koget Susskind staggered fermions, which are also one component, it means that they have a two-dimensional Hilbert space. Why? I could either have the fermion or not have it, no more, right? So at every site, we have a 2D Hilbert space, which is nice. It seems like I can just map it to the 2D Hilbert space of a qubit. So what's the complication then? Can I map operators that are built out of fermionic objects to operators out of the qubit objects? So operators defined on these qubits are essentially these set of Pauli matrices, which are bosonic, right? They're hardcore bosonic operators. But operators based on fermions have different commutation or anti-commutation algebra, okay? So while their dimensionality of a Hilbert space matches, their commutation algebra doesn't. So we have to do something more, okay? In particular, what we would like to have is that, let's call it that phi of x prime dagger to be delta x prime. Okay? So then you may say, okay, what can I do? Can I actually map phi to an operator which is, say, sigma plus, if this is at site x, to a qubit that is associated with site x, and then phi dagger at site x to go to something like sigma minus of x. Can I do that? The problem is that no. If you just pick this, you're not going to be able to satisfy anti-commutations of different sites, fermions at different sites. So it can still work for the same size, but at different sites you don't get your anti-commutations, which is a problem. So then you say, how do I fix this? Well, turn out that you can, one simple fix is the following. You take your phi of x and you map it to not only sigma x of plus, but also the product of a bunch of sigma z's that are sitting at y smaller than x. And similarly for phi dagger of x, you map this to, okay, this is bad notation. This is, let me call these I and j, things like that, so that they're not confused with the x, y, z of the sigmas. Sigma minus j, and then I would call this k smaller than j. Okay. So these are site indices. And this is now k smaller than j, something like this. Okay? So I can do this. Now you ask me, what does it mean? If it's a one dimension, yeah, I can understand. I have a site, and then I have a chain of sigma z before that site. I can easily define that. And if I work out all the commutation relations on-site and off-site, anti-commutation relations, they are met, so that's great. But on the other hand, how do you define this for 2D, 3D, that kind of things, right? So that means that if I have, for example, something like this, I need to define a linear map that goes through all these sites, which means that I could start from site 0, 1, 2, say 3, 4, 5, 6, 7, 8. But I have other choices too. That's fine. Okay, you can go with those choices. So essentially, I'm going like this to define this linear map in 2D, and in 3D you can also define this. So this is how it works. And again, all those computation relations, everything holds. However, something that is a bit inconvenient is the fact that if I have originally local interactions between the fermions, they can turn into pretty non-local interactions. Why? For example, let's say I had a fermion sitting at phi 0 and then a fermion at site phi. So this is a hopping that is nearest neighbor on the lattice. These 2 points are nearest neighbor. But because of my labeling, they are farther away in this linear map. So that if I map it according to this, then I'm going to see sigma of 5 plus, sigma of 0 minus, and then sigma 0z, sigma 1z, all the way to sigma 4z. So I have 5, 6, 7 body operator, which is pretty non-local. So I turn the 2-body operator to 7-body operator in the space of the qubits. So I need to actually hit all these qubits in the system to be able to implement these 2-body operators. In principle, I can get chains of these second sigma z's with length n to the d minus 1. Let's say I have n number along each direction. Then you get chains that could be as large as n to the d minus 1. So volume scaling for the size of these operators is the cost that you have to pay. And I think it gives a very nice perspective, the fact that there is some sort of non-locality associated with the fermions. It's intrinsic to the fermions because of non-computation. So we have to deal with it. And once we do computations, we realize that there's no way out of this, right? However, there is a way out of it. And I kind of already hinted to that in the previous lecture. We trade locality and non-locality by building redundancies. And in fact, so this is a formulation that is called Jordan-Wigner transformation between fermions and bosons, which gives you this non-local, but it's kind of very nice and intuitive, but it's non-local. There are local formulations for mapping fermions to qubits, which use this idea of building redundancies. For example, instead of having only a single qubit associated with my fermions, I can have an auxiliary qubit associated with it. At the same time, I would make sure that I have a set of local constraints between degrees of freedom of auxiliary and the real fermionic fields, such that I can build the Fermi statistics through that. Sounds non-trivial, but it works out very nicely. Essentially what happens is that you can start with these maps, but as long as you have these constraints, you're in a particular subspace of your Hilbert space. Because of these constraints, you manage to really cancel off all these long Jordan-Wigner strings. So these are pretty powerful maps, okay? I'm not going to talk more about that, but it's really interesting that there is this connection between gauge theories and these local fermionic to qubit maps, okay?
Yes. How would you implement a constraint in the qubit system?
You start your simulations in that subspace, and then you hope that you remain in that subspace. That's a good question. If there are errors, does that mean that you completely lost your Fermi statistics, or you just lost it by a little bit? So these are the questions that people are thinking about. But it's similar to the gauge theory, right? If you violate the gauge constraint at one site, does that mean that you're completely off and you don't have the right gauge group? That probably isn't true, right? You're perturbatively away from it. But yeah, so this is the way that it works. You start from a particular subspace, and then you remain there. Yes? You have a question? Did you have a question? No. Okay. Yes?
Are we assuming something about how the qubits are arranged, like all in a line or something?
So here, yes. Yes, we do, and we stick to it. And you get the same physics, right?
So if they were arranged in a sort of 2D like this, then this.
So you could go this way, you could go this way, but there are multiple ways. You just pick a scheme and you stick with it.
In hardware, you don't have to put qubits just in a straight line with nearest neighbor interactions, right? You could have sort of 2D lines.
So usually with algorithmic developments, we assume there is all-to-all connectivity, but that's not reality. For some of these superconducting qubits, they are nearest neighbors, so they have to do a lot of swapping of qubits to make more than nearest neighbor interactions possible. With trapped ion qubits, all-to-all interactions are intrinsic to the hardware. We don't worry about it. So it depends on the hardware. From algorithmic perspective, we assume all-to-all connectivity.
So this is assuming all-to-all.
So this is still a polynomial set of gates required to implement something like this. But it's large. It's volume large. So we want to avoid it.
These tricks for locality, it sounds like what the condensed matter guys use all the time when they factorize some state into a product of states and then invoke a local gauge invariance. So
Yeah, I think
it's the
all
same
of them
idea.
have exactly the same.
Pick up the names they have for it.
Yeah, yeah. Okay, so let's talk about bosons now very quickly. How about bosons mappings? Okay, so no problem with the statistics there. Qubits and bosons have bosonic statistics, so the operators would map properly between the two. However, qubit is a two-dimensional Hilbert space. Bosons are infinite dimensional or large dimensional Hilbert space if we cut them off. So then how do we map them? But there are various ways to map them. Let's say that I have n number of bosons, which is between 0 and lambda, so I cut it off. So this is my bosonic degrees of, it could be electric field as long as I shift everything, right? So you can always do those kind of shifts. It could be your angular momentum. Even if you have half integer angular momentum, you can multiply it by 2, map it like this, and then map it back once you read off your results. So everything can be written like this. So then you define this state associated with this bosonic state to be the following product state of NB. We call this J from 0 to eta minus 1, where I define eta to be the ceiling of logarithm lambda plus 1. Okay? So this is a binary encoding where if this is some integer, I can always write it as 2 to the j, nbj, j from 0 to eta minus 1, where these objects are either 0 or 1. This is just binary representation of an integer, okay? Positive and non-negative integer in this case. So then I would define, I can define this, the tensor product of these 0 and 1s on a bunch of qubits. That, according to this mapping, would give you the state associated with NB, okay? So this is what is called a binary mapping. It's efficient because it only requires logarithm of lambda, number of qubits to store information. But you can also do things like unary encoding, meaning that if you give me an NB, then my state is going to be essentially a bunch of zeros, and only a single one of them is 1, and this is sitting at position NB plus 1 position. Which means that I'm using really lambda plus 1 number of qubits to encode this. Why do I want to do this? It's not efficient. The reason is that if you have, for example, raising and lowering operators in the space of the bosons, that means that you only are acting on 2 nearest neighbor qubits to change the state here. But if you're in binary representations, it might be completely non-loci. You might have to act on all the qubits to change them from 0 to 1. So it's a bit more complicated to do operations in the binary encoding than the unary encoding, but at the same time, it's more efficient. So Usually we stick to with this, but some people like this as well. But. Okay? All right, so any questions? As long as they're quick. Okay, all right, so then let's talk about quantum simulation steps. And whenever I have, okay.
What's your cutoff for the
I guess 3:05 is my cutoff? Okay, so I have half an hour. I was hoping that I would have been done with this topic already so that I can talk about this. Anyway, I'll share my notes, so hopefully you'll see more details. I'm going to be very quick with the quantum simulation steps. Okay, so...
If you think we can sort of assume that quantum simulation is possible and focus on the gauge theory aspects, just your judgment.
Yeah, but I have to say a few things so that you can understand why the cost is whatever it is that I'm going to say. So that's a good point. I can just focus on aspects here that are important for this talk, for this part. So the steps really in a nutshell the following. I have a bunch of qubits that are encoding my fermions and bosons or whatever physical system that I have. But usually it's easier to start in a simple product state, all zeros. But then that means I have to prepare non-trivial states. Okay, so state preparation is the stage 1. Then once I have the state that I like, presumably I want to do some time evolution. For example, you want to simulate a scattering process in gauge theories. You have to prepare your hadrons with certain energy. You need to time evolve them into the future, see what happens. And in the end, you want to measure. So physics is here. So we have to know what we are after and then be able to prepare the right quantum circuits, the right strategies to extract that physics. Okay. So state preparation. So I'm going to be very quick. How do we prepare non-trivial states? Unfortunately, this is not a guaranteed success over here. Okay. Preparing, for example, ground state of K-local Hamiltonians turn out to be what is called a QMA hard or QMA complete problem, meaning that it is really the quantum equivalent of NP complete or probabilistic NP complete. So there is no guaranteed success in state preparation, meaning that with polynomial time, we don't know whether we can, with a given accuracy, prepare that state. That hasn't stopped us from building more efficient heuristic algorithms, can do various tasks. And usually we're not interested in an infinitely precise state. Something with some approximation of that state can still be very useful in various tasks. Okay? So if you give me that accuracy, I can build different algorithms that can build it. So what are the few algorithms that people have been looking at? Adiabatic state preparation is one of them. So what you would do is that you start with the ground state of a simpler Hamiltonian. You adiabatically change that Hamiltonian to the Hamiltonian of interest, and you're hoping that you remain in the ground state manifold. Of course, that can break down if you have phase transitions, the gaps would close, and so on, which obviously could be a problem for QCD. If you start from the quarks and gluons in the free confining phase, how can you get to the confined asymptotic states of the theory? That's the question, right? So it's not always efficient, but it's something that people have tried, okay? So what else can you do? You can do imaginary time evolution. Okay, so you start from some state that is not a ground state, but hopefully it's easily prepared. And then you hit it with e to the minus h tau, where tau is real. Okay? Can you do that on a quantum computer? In principle, yes. it's a non-unitary operation, but you can always embed it into a larger unitary. It means that you need a bunch of enchiladas to do that, but you can do that. And then, is it better than this? I would say.
What does it mean?
This one?
You just said you could do this.
We can do this on a quantum computer despite the fact that this is a non-unitary object. You encode it, so you have e to the minus, somehow you encode a function of h over here, and then you have another sector. And this whole thing is just a unitary operation. So there's an art in defining what that unitary could be. So once you do that unitary operation and you trace out in the end this ancillary subspace, then you end up with a non-unitary operation on the rest of the system. That's the idea.
Purification of the states.
Yes. I guess in the condensed matter we call it purification, for example. So you can do this. You can do something like this. The good thing about this procedure is that you can very quickly, exponentially fast, die off all the excitations, right? We take advantage of this essentially in the Monte Carlo simulations, right? We have a transfer matrix in Euclidean time, and we use this trick to get to the ground state. Here we can actually have a Minkowski ground state in a quantum computer using this trick. But again, it can be costly because this is a non-unitary operation, so it had to be encoded into a unitary, and that's not very near term. What else can we do? We can do something called variational algorithms. This is not completely quantum algorithm. It's a hybrid classical quantum in a sense that you start with a simple state, psi 0. You use a quantum circuit that is parameterized instead of a bunch of parameters theta I, such that you end up with a more non-trivial state than you started with. You measure expectation value of your Hamiltonian in that state. It would be a function of these theta i's. You try to minimize it, and then you go to a feedback loop over here to start with a different set of parameters based on that classical minimization. You continue this process.
Just trying to find the ground state of the system.
Exactly.
It's not good for scattering.
You can still use it in the context of hadronic state preparation. You have to come up with a variational circuit that would prepare those hadronic excitations. And I can point you to the papers that have used this trick to also prepare things like, because a hadron state is really sort of the ground state in baryon number 1 sector of the QCD, right? So you can always, once you find the ground state, you can orthogonalize to that state.
That can be done by Monte Carlo. You don't need quantum computers for that.
Monte Carlo would not give you the Minkowski wave function, right? It gives you a set of energies. It's going to be the Euclidean time distribution of these gauge variables. This is, it's not clear how you convert that description to a Minkowski wave function.
This is used to prepare in states.
Yes, yes. So again, I can point you to some papers on that front. Okay, so this is really a hybrid classical quantum, but the good thing about this is that it can give you very shallow quantum circuits, and it can be very robust to noise. The bad thing about this is that there's no guarantee. You may get stuck in local minima. You may have situations where you have a sort of a manifold with a gradient that is exponentially flat, sort of in system size and situations like that. So it is not guaranteed that it would always work, but people try it in the gauge theory context as well. And then it was mentioned, so there are things that are called near optimal algorithms. I'll talk a bit more about these algorithms in the time evolution part, but you can use those near optimal algorithms for time evolution to be able to project to the ground state. What does that mean? If I can find some function of Hamiltonian, for example, similar to this function, but it doesn't have to be this function, it could be something simpler. that once I hit any state with this multiple times, I progressively project into the ground state. This might remind you of these Krylov methods in classical computing for finding lowest eigenvalues and eigenvectors of a matrix. This is very similar. You can also do those kind of methods in quantum computers, okay? So projective methods. You can also use classical methods. David already sort of asked these questions. The way that this could work is that, let's say I do my Monte Carlo and I learn some information about static correlation functions, structure functions, energies. As long as I have an efficient polynomial size ansatz for Minkowski wave function, I can optimize that wave function based on those classical static information. Okay, that's important. It has to be polynomial size. If it's exponentially large wave function, which means I can never reproduce the wave function exactly, but just approximately, this could work. You can use tensor networks. Those are efficient representations of quantum wave functions. They usually work in lower dimensions, so not very practical for higher dimensions. But those also would give you efficient representations of a quantum circuit that generates a wave function for you on a quantum computer. So there are more details about this in the notes. So that's all I wanted to say about state preparation. Okay, if that's quick.
So we said state preparation in general is not efficient, whereas implementing arbitrary unitary is efficient.
Yes.
Can we not take the state that we want to prepare, put it inside a unitary matrix, and then efficiently get that state?
How do you find that unitary?
How do you what?
How do you find that unitary? Give me that unitary from the sky. I'll find a way to circuitize it. But what's that unitary that prepares this state? That's the question.
Okay, so the state that you're trying to prepare is not defined as an explicit
You just have a Hamiltonian. I don't know what the ground state of that Hamiltonian is, right? Yeah, exactly. Other questions?
Can you project onto
Excited states?
yeah, is there how robust is that to noise?
It depends on the problem, it depends on the hardware. But yeah, you can always project to the progressively to the next excited state by orthogonalizing to the state that you already found.
Okay.
So that's possible.
And it's not some like totally unstable thing where you get an error and you just go right back to the ground state.
Depends on the gaps, depends on the method, right? So if you're using something that is more adiabatic, the gaps are very important. So it really depends. But yeah, it could be hard if you're dealing with very dense spectra, just as with classical computers. Okay, so time evolution. Okay, so there is demonstrated quantum advantage in implementing time evolution operator e to the minus IHT. Why? Because it's a unitary. And as I told you, there is a finite set of sequence of gates that can implement any unitary in principle, okay, efficiently. And remember, I'm encoding an exponential Hilbert space using qubits. So there's already that encoding efficiency that is in there, right? So I get a logarithm advantage in encoding the degrees of freedom, or the Hilbert space already out of that. So how do we then deal with this? There are ways to simulate or digitize the time evolution operator. One way is to approximate this with product formula associated with this, which is, in this case, let's say my Hamiltonian is a sum over I from 1 to gamma of some number of terms. These could be non-commuting terms. So then I can approximate this operator with e to the minus I h1 t all the way to e to the minus I h gamma t, such that I do this decomposition so that I know how to decompose each of these terms separately into those universal set of gates. If you give me a big, complicated Hamiltonian like QCD Hamiltonian, there's no way to figure out how to decompose that into a set of gates unless you do something exponentially inefficiently. If you want to come up with a polynomial size algorithm, you better use tricks like this, which means that you break up the terms to the point that you can realize a polynomial size circuit for each of these things. Obviously, there is an error associated with this. So I'm going to call this a Trotter error. So what we want to do is to make sure that V1 of t minus e to the minus iht norm is bounded by some error that I set on the simulation. Okay? So for example, if I'm interested in simulation for big time t, then what that means is that I have to find for smaller steps what this is. And in fact, people have found tight bounds on what the error associated with these product formulas are. For example, for the first order product formula, which is this guy that I wrote here, there is the following bound, hi, and then sum j from I plus 1 to gamma hj. So it's essentially the sum of the commutator of all non-commuting terms that encounter there. Okay, so it is bounded by this amount. All right, so if I call this some alpha of p, which we can compute, right? This is just a set, or at least we can bound. Then I know what the error associated with the smallest steps are, and then I can put it in these largest steps. So that means that in order to reach this total error of epsilon t, the number of Trotter steps, the number of times that I have to repeat putting these things together for a small time steps is going to be equal to, so for the piece order product formula, it is going to be epsilon t associated with that piece order, alpha of p, and then t to p plus 1 to the 1 over p. So for first order product formula, it goes like t squared over epsilon. And then for second order Trotter formula, which means that I have these guys, and then I have these guys in reverse for half of the time. So that's the second order. Again, I'm being really rushing this. All the details are in the notes. For the second order, you get 1 over square root of epsilon, which is nice. It's also like t squared. So you get improvement as you go to higher orders, but obviously then you have to implement more of these operators for each of those steps. So eventually, you get a linear scaling. If p goes to infinity, you can achieve a linear scaling. So this is, I think, total time t. Linear scaling out of this. But at the same time, you have p number of these terms on each Trotter step to implement. So it's not really good. So you have to find the balance of a high-order Trotter formula or product formula such that you have a limited number of terms to apply, but you have a good control over the error. So this algorithm does not reach the linear scaling unless p is infinity, which is not efficient. But there are near-term or near-optimal algorithms where they have, for the time evolution, there are near-optimal algorithms, meaning that they do a scale, so the time complexity would go like linear in time and logarithm in 1 over epsilon. They are more complicated circuits. They require more Enshila qubits and so on. They sometimes go under the name of qubitizations, singular signal processing algorithms, quantum locks, and so on and so forth. There's a bunch of different strategies that are beyond what I just said here. They are near optimal, but they are more complicated algorithms. Okay, so asymptotically, you reach your linear scaling, you reach a logarithmic dependence on 1 over epsilon, which is good, compared to these product formulas, but those are more complicated algorithms. Okay? Can I do better than linear scaling in time? In principle, not for a quantum Hamiltonian. Otherwise, you can fast forward in time or not. So that's the best that you can get. Anyway, so measurement, I just say a couple of words about this, and then I'll tell you what the simulation cost of QCD is. Okay. So measurement. Well, if I want to measure the entire wave function, that's not efficient. There are exponentially many amplitudes to measure. Even if I have a quantum algorithm that gives me access to it, how do I store it in a classical computer, right? Those bits. And so that's not good. We don't want to do full state tomography in general for these large size problems. So we have to pick the physics that we're interested in, the quantities that we're interested in, and be able to efficiently access them. So what are the few things that we could access? We could access energy, momentum, particle number, charge, you name it, both locally and globally. These are essentially local or semi-local correlation functions that we can measure. So we don't really need access to the entire state, we just measure a bunch of correlation functions that are local. Energy measurements, we can also use something called quantum phase estimation, which uses quantum Fourier transform. It's really efficient. There's quantum advantage in it. So these kind of quantities we can access. Okay. What about correlation functions in general? Yes, we can do this. How do we do this? Let's say I'm interested in the following. Okay, so you have your state and you want to measure an operator in that state. So this is a bunch of qubits associated with that state. You introduce an Anshila qubit. You started in 0. You make a superposition of 0 and 1 by this Hadamard gate. And then you do something like this, and then you measure either in the X or in the Y basis. Meaning that you either insert another Hadamard, and then you measure the 0 and 1 probabilities of your qubits, or you put in phase gate and a Hadamard, and then you measure the 0 and 1. The details are in the notes. So what happens is that with some probability you get 0 on this qubit, with some probability you get 1. It turned out that if you subtract those probabilities, that gives you the real part of this expectation value. And if you do the Y measurement, so that was for X measurement, if you do the Y measurement, you get access to imaginary part of that expectation value. So you have access to the whole thing. Importantly, if this would have been a time-dependent operator, so time-dependent correlation function, let's say if I had an OT, O prime at some site, or a qubit N prime 0, what about something like this? Well, we can also do this because I can write this in the Heisenberg picture as O0. I can insert time evolution operator over here and over here. And this is one of the operators, this is another operator. And with something like this, you can also measure this. So this is all really sort of the circuitry tricks called a Hadamard test. And there's your Hadamard here that would then give you access to real and imaginary part of a time dependent. And I already told you how to deal with things like e to the minus IHT. So that's a routine that we can efficiently implement.
Sorry, just to make sure I understand correctly, these are like control O gates? So
yes, these are controlled.
That's how you get them.
Exactly. So it means that if you start from 0, you have a superposition of 0 and 1. Meaning that half of the times it could be that nothing happens, half of the times this could be implemented. So that's why you can get, yes?
Okay, if you remove the last e to the minus IHT box, will that affect the measurement?
It doesn't, but I'm keeping it in case I'm going to do something more in the circuit with this. Okay? And this is a very nice trick. It allows you to not collapse the wave function and continue with it by just measuring this ancillary qubit. Okay? So using these ancillary qubits is very important in doing quantum computation. Yes?
What would a circuit look like if you just wanted to measure, say, the real-time decay of a particle? So if you just set up a heavy particle, you have a theory with two light particles, and there's a...
Yeah, and then you let it time evolve. That's
yeah,
it.
so what, does it look just like this? Like you just measure...
Okay, so that's a good question. Let me say S matrices. That was the next thing that I wanted to say. Can we measure S matrices? That's what we're interested in quantum field theory. Yes, we can. An S matrix is essentially some psi in, out, or out, in. Okay, can we measure the overlap between two different states? So in this case, you start in whatever your initial state is, this heavy particle, and then that's one of your register would be that. You just prepare that state. Okay, so I would call this the psi in register. Another one is that you prepare psi in, but you time evolve it, do all sort of things, and you get your psi out. So psi out is really psi in time evolution, right, up to some point. And then you can use this Hadamard trick to be able to measure something like this. So in this case, you introduce an ancillary qubits again in 0. Then you have a Hadamard over here. And then let's say that this is a box that prepared the psi in out of some initial state. This is the box that, I'll put it over here, that prepares the psi out. So this is the in preparation, the out preparation. And then you have two control over these. So you either prepare them or not prepare them, depending on the state of this guy. And then you measure in X or Y basis in this qubit. So then you get access to an overlap like this. So really doing things like exclusive processes amounts to not only preparing the initial state, but also the particular final state that you're after. So it's more expensive. If you want to do inclusive processes, you can also do that. You can have your currents, and then you can, for example, look at this expectation value inside the proton. Okay? You prepare your proton states, you use the same tricks that I talked about to get access to these non-equal time correlation functions of the currents. And I use the Hadamard test to measure this expectation value. Then you can process this to get things like out of optical theorems, like inclusive processes. Yes?
So I'm kind of confused. So I would think of an S matrix like those out-in states are asymptotically late time
Yes.
observables.
Mm-hmm.
But I was really asking, could you measure in real time the decay of the state? So like there's, you know, this thing where you don't have, you're supposed to have quadratic time dependence at very short times. I was just wondering if you can explicitly see that and what the circuit would look like to measure, you know, let's say I prepare, I don't know, a neutron or something, or just see it decaying slowly as a function of time.
Yes, you can. Okay. Yes, you can. As a function of time, you can measure things about that state. That's really the beauty of it. You can, in terms of like the in and out state, you can prepare two wave packets, you can collide them, and then right after the collision, you can measure some properties of that state. If you're interested in thermalization dynamics, you can look at things like entanglement structure of that state, which you can do efficiently. If you're interested in hadronization mechanisms, you can define your observables and just like measure after the collision. You don't have to wait until you go to the asymptotic states. Absolutely. That's the power of these real-time methods that we don't have access to. If you just think about asymptotic S matrices, we miss on some of these interesting physics. But yes, you can do those, right? Can I actually take the questions after? Because it's not just that I'm going to keep you, I'm going to miss my flight. Okay, so now that you have a notion of what it takes to simulate a generic theory, let me tell you what it takes to simulate QCD. I'm going to give you just a few numbers, and you're going to see a little bit more details on the notes about where those numbers come from, okay? So I'll keep this and this, and these ones we don't need. Entanglement is another observable that, or not observable, quantity that I mentioned in the notes, and I tell you why we can measure it and what kind of things we can get out of it. That's something that classically we don't have access to, so that's another really fun part of quantum computing that gives you beyond the kind of quantities that we measure in our classical simulations or even like LHC experiments, right? We have access to more in principle. Okay, so what does it take to do QCD? So SU3 lattice gauge theory in 3+1D with all the flavors of the quarks and everything, okay? So there are a few caveats for the numbers that I'm going to mention. The first one, these will not include a state preparation part of the algorithm. We don't know what it takes to simulate a proton yet, an actual proton with a TeV scale energy. We have a few ideas for simple gauge theories, lower dimensions. We've tested a few algorithms. As a community, there are a bunch of things that have been tried. But in terms of really guaranteed success with these algorithms, we don't have it. So let's just not, let's keep it clean so that we have something that we can actually bound in terms of the error. And later on, we'll see some of these state preparation algorithms depend on the time evolution routine. So as long as I can figure out what the cost of that operation is, it could be of the same order if I use that routine for a state preparation, for example. The same with measurements. As you saw, some of these real-time dynamical correlation functions require the time evolution operator. So it's good to actually think about just the time evolution and cost that aspect, okay? So what does it take to do e to the minus IH QCD in the Kogan and Susskind formulation? And I'm going to focus on Kogan and Susskind formulation, and I'm going to focus on electric bases or irreducible representation bases. So we can do this through product formula algorithms. You can do it at first order, or most of the papers are about second order product formula algorithms. And remember, the error would go like T, what's over there, 3/2 over the square root of epsilon, okay, for the second order Trotter formula. Okay, so the very first paper that actually looked into this, you may be surprised, was 2005, even before all this quantum computing vibe was there. So this was by Burns and Yamamoto in 2005. And they wrote down all this Kogan and Susskind Hamiltonian. They talk about these operators, what they do, and their action on the basis of states and everything. But in the end, their algorithm is kind of the most naive thing that you can imagine. Why? Because they say, all right, give me these Hamiltonian operators. I decompose it into a set of Pauli matrices. You can always do that, right? So if you have a register of size n, and you have an operator that is defined on that register, something like this, you can always decompose it in terms of a set of Pauli operators defined, sigma z, sigma x, sigma y, on those qubits. So I can have 4 to the n number of Pauli operators that are associated with that unitary. That's the most naive thing that you can do, but it's exponential. Okay, so in this particular QCD problem, it turned out that, well, you have, for example, for the plaquette operator, you have these U operators. Each of them is at least 12 different operators. And by the way, they have a Hilbert space that is like NC squared times logarithm of lambda, right? Because they're NC squared minus 1. There are 8 colors or 8 registers, and each of them is of size logarithm of lambda. Now there are 4 of them, so that's 4 times this number, just for this particular operator. And now you have 4 to this number, which is the number of Pauli operators that you have to do. So your algorithm is going to be really bad in terms of the number of terms. Even for a lambda that is, I think, equal to 4, you get something like 10 to the 40. 10 to the 38. 38. Okay, so that's just the number of terms. Now, there are 10 to the 38 terms, and then you have to exponentiate it, and you get a bunch of Trotter errors that you have to account for. So forget about it, right? So this is like this naive approach, forget about it for QCD. So what else can you do? So then it came in 2020, or 21, this paper, this nice paper by Can and Nam, 2020 or 21, where they say, okay, let's not do this naive decomposition. Let's find a block diagonalization of the whole exponential that we can then write in terms of elementary set of gates. For them, in order to do that, they have to take each term inside these U operators and then separate them to even and odd subspace, or 2 disjoint subspaces. Okay? It turned out that their algorithm then, so instead of Pauli decomposing the whole thing, they find a way to exponentiate e to the minus I each of those terms times t. Okay? So then the algorithm has the following scaling. So the number of terms is 12 times 3 times 2 to the nc squared minus 1. That's about 10 to the 15. So much better. But it's still not too good. Remember that then you have to trotterize. There are these terms separate, and then the trotter error will give you that you actually have, out of that alpha p that is here, you get a number of terms to the 3/2. Okay, so there is also that number of terms that shows up there. So that means that already from that, they have about 10 to the 23 or 24 prefactor. And each of those circuits come with their own associated costs. One of the important costs is to evaluate these Clebsch-Gordon coefficients. So that's already very expensive. So when all comes together for a simulation of a lattice of 10 by 10 by 10 with a lambda which is equal to 10, with an epsilon that ranged from 10 to the minus 1 to 10 to the minus 3, with a lattice spacing that goes from 1 to 10 to the minus 1. If it's wrong, then we'll check the notes for, I think it's 10 minus 2. What else? Okay, so these parameters and the simulation time in the order of the volume. Okay, so you can evolve the entire lattice essentially. You get a number of T gates that scales like, or is of the order of 10 to the 49 to 10 to the 43. Okay, so there is this factor, and there is also the cost associated with calculating each of those terms individually, which amounts to calculating functions that are square root functions of quantum numbers, and that's also very expensive. Okay, so it's not very good, right? Number of qubits? Any guess? 10 to the 11. Okay, so
this may be irrelevant, but I mean, assuming you're not using any Gauss law constraint here at all.
no,
so
this is just that.
It's just, yeah,
Okay.
in the noise.
All right, so one thing to note that is classical computing, supercomputers. Do you know what's our supercomputing power? So we're in an exascale era of quantum computing. That means about 10 to the 18 floating point operation per second. Okay, so that's kind of the number that we're talking about in terms of the number of gates. If we had a quantum supercomputer of that size, that's the number. And in terms of the memory, I think we're talking about petabytes or a few hundreds of petabytes anyway. So 10 to, say, 12, 15, whatever. This is kind of the range. Okay, so I think if we are lucky and we have quantum supercomputers, qubits, probably the number of qubits would not be a problem, but definitely we need to improve this number. Quantum chemistry problems, they're talking about 10 to the 15 to 20. So that's reasonable, more reasonable. It's still not near term. So I'm going to tell you that there's been 2 developments just in the past few months. One is using product formula. So this is by myself and Jesse Stryker at Berkeley Lab, where we improve this number, this 10 to the 24, by at least 13 to 14 orders of magnitude, by a better block diagonalization algorithm compared to this one. So that's one thing. Probably more importantly is a paper by, let me put the names, Rode et al. From 2024, where instead of product formula algorithms, they use the near optimal algorithm. Remember, the near optimal algorithms have a linear time scaling and logarithm of 1 over epsilon. And importantly, they don't have to deal with block diagonalizing the whole exponential. They can actually encode the Hamiltonian term themselves and then evaluate functions of those. So they don't have to deal with the number of terms as we do with the product formulas. For the same simulation, they report 10 to the 27 to 10 to 28 qubits. And the same number of qubits, almost, which is good. So without compromising on the number of qubits, they already reduce this number, which is already reduced to something smaller, even more. Okay, so you see that we are really in the age where we can start from the most naive things. They're not going to work, and then within a year or 2, we can improve things by 20 or 30 orders of magnitude. So that gives me hope, okay, that we can still do better. There are a bunch of things that we can still improve, and I have mentioned those in the notes. So maybe we get to the point where 10 to the 20, 15, 20, and we get our quantum supercomputers and we can do our QCD, amazing QCD problems. That's the hope. All right. Thank you.
Okay. Are there further questions before Zohreh needs to get on?
I don't want to hold up your plane, but...
No, I think I have another 5-10 minutes.
Finite temperature, if you wanted to do that. With
Yes, very good.
How would that look like?
Yes, so you can do thermal state preparation. So I didn't mention those techniques, but you can use tricks. You can even use variational quantum circuits to prepare thermal states. You can use imaginary time evolution to prepare thermal states. We have tested these methods for gauge theories. They work. There was a recent paper from a month ago, a trapped ion quantum computing paper, where they did a phase diagram of 1 + 1 dimensional QCD with finite density, finite temperature. So a very small system. So yes, we can do those problems. In fact, if I had time to show those slides, I can post it on a Slack. You would have seen some of these nice plots that come out of quantum hardware.
You can drop
on the Slack, yes.
The slides on Slack.
Yes.
Maybe that's a generalization of Graham's question. Are there front-runner candidates for the physical realizations of qubits and gates that are more suited for these simulations?
For our simulations? So, a very interesting, exciting topic that I didn't even mention are these more hybrid analog quantum, digital analog quantum computing approaches, where you can have bosonic qubits. As opposed, you can have fermionic qubits, you can have bosonic qubits. You don't have to just have qubits. You can have bosons and fermions as the encoders of information. Wouldn't that be amazing if my gauge link could have been just implemented without any cutoff, right? So those are technically harder, but there are now candidates and there are simulations where people have demonstrated the ability of these bosonic and fermionic digital quantum computers to do things. So I think that's another direction that might completely change the landscape. We're very limited in terms of thinking about bits or qubits, 0 and 1, because that's closer to classical computing. But quantum computing is an entirely different world, and it's very possible that in 20 years, all these schemes that we think about today are out of the picture. We're thinking about really physical quantum computing.
And in terms of buzzwords, I hear about limitations like decoherence time for qubits. Those systems, how do they compare to other trapped ions?
So the qubit-based systems are still better because there's been 20 years of developments behind them, right? So it might take a while before bosonic quantum computers or fermionic quantum computers get to the same decoherence times. But that's what I'm saying, it's the future. But in terms of the current quantum computers, trapped ions, superconducting qubits, they are the primary candidates that are in the market and been really showing interesting results.
Let's see, Ryan.
How much of the overhead can be dropped if you don't focus on realistic QCD? So if you did, I don't know, some candidate toy model or something, let's say in 3+1 dimensions, but it's not QCD.
Yes, that's a very good question.
How much do these numbers drop, basically?
So what we're thinking about today is that if someone would give us 100 to 200 qubits, which is realistic, right? IBM would give you that, and trapped ion systems soon will give you that. 100, 200 qubits is 2 to the 100 Hilbert space, right? So it's not going to fit the QCD problem, but some interesting, strongly interacting quantum field theory, right? Where we want to look at non-perturbative effects in real time. Can we learn something from that? Mm-hmm. And in fact, we're working on this. We're looking into spin systems that have confining dynamics and looking at things like string breaking, hadronization in that context in real time in the quantum hardware. So those are the problems that we're going to focus on the next 10 years, maybe more, before we have these large super quantum computers. Definitely.
Okay. And Rachel?
What happens to those numbers if you set lambda equals 1 or 2 rather than lambda equals 10? I mean, obviously it won't be a good simulation.
So I didn't write down the scaling of this product formula algorithm. So there are a bunch of factors. One of them is lambda. One of them is logarithm of lambda, a bunch of other factors. So just figure it out. Yeah.
Okay. I think if there are no more questions, then let's thank Zohreh again.